Hi Rockridge, this is Mrs. Berger, and today we will be talking about combinatorics. Combinatorics will come to us in three different ways. The first way is something called the fundamental counting principle. The fundamental counting principle basically says if something can happen m different ways, and something else can happen n different ways, if we multiply those ways together, we'll find out the ways that both of them can happen at the same time. I kind of like to call this my meal deal. So if you've got a meal deal or you're combining sets of different things all together to see the ways that they can happen together, then you'll be using the fundamental counting principle. So let's look at a couple of examples. So here in example 1, we literally have a meal deal. The restaurant says choose from a list of 3 appetizers, 7 entrees, and 5 desserts, and come up with a meal for yourself. How many different meals could you come up with for yourself? Well, the way you would do that using the fundamental counting principle is the 3 different ways appetizers can be chosen, times the 7 different ways entrees can be chosen, times the 5 different ways desserts can be chosen. So that gives you a total of 105 different meals you could create for yourself. Let's look at the next example. So on the next example, we're talking about Texas license plates. We want to know the different ways that you could have a Texas license plate, how the different ways these letters and numbers could be combined to produce one license plate. The license plate can have 1 letter followed by 2 numbers followed by 3 letters. The first question asks, how many different license plates could you create if you are allowed to repeat letters and digits? So let's do this option first. How many different letters in the English language? 26. How many different numbers? 0, 1, 2, 3, 4, 5, 6, all the way to 9. That's a total of 10 different digits that you could have in this place right here. And then another 10 different digits because we're allowed to repeat those. 26 letters for this position because we're allowed to repeat. 26 letters for this position, and 26 letters for this position. So if you multiply all of these together using the counting principle, you'll find out all the different ways a license plate could occur. This comes out to be over 45,697,600 different plates. That's how many cars you could support in Texas. Now, let's ask the question if we are not allowed to be repeating numbers or letters. Same positions available on the plate. Letter, number, number, letter, letter, letter. In the first position, we have 26 letters. In the second position, we have 10 digits. In the next position, it's another digit, but we've already used 1 that we're not allowed to repeat. So we're only left with 9 choices here. In the next position, we have only 25 letters left to choose because we used 1 already. 24 letters left for the next position, and 23 letters left for this position. So the fundamental counting principle states that we could have 32,292,000 plates if we weren't allowed to repeat letters or digits. Let's look at permutations. In a permutation, we're looking at how many different ways we could order things. So we could order teams finishing an Olympic bobsledding competition, or placing posters on a wall, lining people up for a picture, lining them up to get on a bus. All of these are different ways that you could order objects. The formula for this is n factorial. So think about it this way. If you have 10 teams competing in a bobsledding competition, there are 10 different places. First place, second place, third place, fourth, fifth, sixth, seventh, eighth, ninth, and last place. How many different ways can they finish this race? Well, there are 10 teams that could possibly fill this. But once that team is placed there, only 9 are left to take second place. And so on and so forth. When we decrement each spot by 1, 10 times 9 times 8 times 7 times 6 times 5, etc., this is called factorial. N factorial. So the answer to this question is 10 factorial. We actually have on our calculator a function that we can use to do this for us. It's in our math menu, in the probability section. See the factorial here? We first have to enter our number. 10 followed by the factorial. Math, prob, choice 4. 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 equals this number here. 3,628,800. 3,628,800 different ways that this bobsledding competition could end. Now, what if we only care about the top 3 finishers, the gold, silver, bronze medalists? That's easy. We just take the first 3 positions in this order. We don't care about how the last ones finish. So in first place we had 10 options, in second place we had 9, and in third place we had 8. So there are 720 different ways we could get gold, silver, and bronze medalists in this race. This is considered a permutation of n objects taken r at a time. We have a helpful function on our calculator for this as well. The notation for this is n, permutation of n, choose r. So the number of objects, so in the last example we had 10 different finishers, 10 different teams competing, and we cared about the top 3. R was 3. So NPR, the formula for this is n factorial divided by n minus r factorial. This formula is given to you on the SOL. We have an even easier way to find it on our calculator. We'll look in our math probability menu again. Let's look at this horse show competition example. Again, we care about the top 3 winning horses. We care about the ones that win the grand prize. So the first place, we have 12 different ways, 12 different horses that could finish first. Once that horse wins, we have 11 that could place second, and we have 10 that could place third. So we have permutation of 12, choose 3. The function on our calculator is found in the math menu, math, probability, NPR. We had 12 horses in the race, and we cared about the top 3 finishers. There are 1,320 ways that could happen. We also could have done this formula up here to do that. We could have done 12 factorial divided by 12 minus 3 factorial. It will get us the same answer. Now let's look and see, in a case where order still matters, but we've got some repeats that help us, that give us a hard time to distinguish the differences. So for instance, if you wanted to know the many different ways that you could rearrange the letters in Miami, but since we have repeats, if we rearranged 2 of these letters, the M and the M, we couldn't tell the difference, whether it was the first M or the second M. So we say, what is the number of distinguishable permutations? In order to figure that out, we will need to divide out the repeats. Let me show you how that's done. Let's first count the number of letters. 1, 2, 3, 4, 5. So initially we'll think there are 5 factorial different ways that the letters could be arranged, 5 different positions. 5 times 4 times 3 times 2 times 1 for all the different positions. Now, we need to divide out the repeats. We have 2 M's that are repeating and 2 I's that are repeating. And so to take those out, we divide 5 factorial by 2 factorial times 2 factorial. When you do that, 5 times 4 times 3 times 2 times 1, divided by 2 times 1, divided by 2 times 1, you'll get 30. There are 30 different ways to arrange the letters in Miami that are distinguishable from one another. Let's look at Tallahassee. There are more repeats. The T doesn't repeat, but there are A's that happen 3 times, L's that happen twice, the H happens once, there are no repeats, the S happens twice, and the E happens twice. How many positions are in this word? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So without taking into account the repeats, 11 factorial is the different ways that you could arrange the letters in those orders. Then we'll factor out, or we'll divide out, the repeats. 3 factorial times 2 factorial times 2 factorial times 2 factorial. This comes out to be 831,600. If you need to pause the video to make sure your calculations come out the same, please do. Now let's move to the concept of combinations. In combinations, order does not matter. Order is not important. So for instance, if you're playing cards, you don't care what order you get the aces in, you just want the aces. There's a formula for this as well, the number of different combinations that you can get. N is always the total number of objects involved, and R is always the subset that we're looking for. And the formula is n factorial divided by n minus r factorial times r factorial. This will be given on your SOL formula sheet, but we again have a function in the probability menu, math probability menu on our calculators, that will make it even easier. So let's look at our first example. A standard deck of 52 playing cards. We want to know, if we don't care about the order in which we get the cards, how many different 5 cards can we have? So we're saying, what is the combination out of 52 cards that we can get a 5-card hand? So we can either substitute 52 for n and 5 for r, or we can make our calculator do it for us. Math, probability menu, NCR, choice 3. We had 52 cards, and we want a combination of 5 of them. That's how many different ways you can get those 5-card hands. 2,598,960 different hands. That's why card games are so exciting. That's how many different ways you can get a 5-card hand. So now let's look at a more complicated problem. In how many 5-card hands are all the 5 cards of the same color? So let's first look at this into 2 parts. All of the same color. Hopefully you know that there are 2 colors. There are red and there are black. So what we're first doing is we're saying, out of 2 colors, we're choosing 1 color. Then we're saying, once we get down to that, remember we have 52 total cards. And how many are all 1 color? 26 are all 1 color. So out of those 26 different cards in that 1 color, we're trying to choose a 5-card hand. This is like a counting principle problem. Whatever 1 out of 2 colors and 5 out of 26 cards multiplied together is, that's our answer. So the answer to this is, there are 131,560 different ways. If you need to look at this differently, think about it this way. You have a combination. Out of 26 black cards, you could get 5. Plus, out of 26 red cards, you could get 5. We're going to add those 2 different options for combinations together. And again, you'll get 131,560. Either way you look at it, you'll get down to what you need. 5-card hand of blacks, or a 5-card hand of reds. Those are all the different combinations we could have. Let's look at the next example of combinations. If Shakespeare wrote 38 plays, and we can divide those into 3 genres, comedies, histories, and tragedies, how many different sets of exactly 2 comedies and 1 tragedy could you read? So we're saying 2 comedies out of how many comedies? Out of 18. And we don't care what order we read them in, we just want 2 of the 18. So 2 of the 18, and we need to also, in this one event, we're reading also a tragedy. So we need to read 1 of the 10 tragedies. So again, this is event 1 happening times event 2 happening, using counting principle, fundamental counting principle. So this gets us 1,530 different sets. Now let's look at this in a slightly different way. If we're looking at how many different sets of at most 3 plays that you can read, regardless of the type, how would we solve this? Well, let's see. We're looking at 3 of the 38 And once we read that, those 3 different plays out of the 38, we're left with possibilities of 2 of the 38. Remember the word at most, meaning we could read 1, 2, or 3 plays. So we could either read a combination of 3 out of the 38, or we could read a combination of 2 of the 38, or we could read a combination of just 1 of the 38. That's how many different ways we could meet this need of at most 3 plays. So we would evaluate each of these using our calculator and sum them up. So this happens 8,436 different ways, because it's a combination of 3 of the 38, and there's so many different ways you could combine those to make a group of 3. Only 703 different ways to get a group of 2, and only 38 ways to get a group of 1, right? There's 38 plays. So if we were to add those all together, 9,177 different ways you could read 3 of the plays, regardless of what genre they were. Alright, so let's run through some group practice. I won't run through all of these. This is really just to get you familiar with your calculator, so we'll just do a couple of these together at the top here. So the first one, 5 factorial, just make sure you know where to find that in your calculator. 5 factorial, which is, of course, 5 times 4 times 3 times 2 times 1. So I would do 5, math menu, go over to probability, choice 4, enter. That's 120. You can do a couple of these on your own. The key is online for you to check yourself. Now, a permutation, 4 out of the 6 total. Remember, this was a problem for order matters. So this is a problem in which order matters, and I would choose choice 2 here. And it was, out of 6, we're choosing 4. Out of 6, we're choosing 4. 360. This one, and again you can practice these on your own. This one, 5C3, that means out of 5, we're choosing 3, and we don't care about order. So math, prob, choice 3. Out of 5, we're choosing 3. 10 different combinations. 10 combinations. So let's take a look at a couple of examples here. Alfredo is getting dressed. He has 4 clean shirts, 3 clean pants, 2 pairs of clean socks. How can he do an outfit? How can he make an outfit of a shirt, a pant, and a sock? So he has 4 different options for shirts, times 3 different options for pants, times 2 different options for socks. This is a counting principle question. So he could come up with 24 outfits from what he has left that's clean. Let's look here. Postal Service uses zip codes, and they're 9 digits. 1, 2, 3, 4, 5, 6, 7, 8, 9. Assuming no restrictions, and what this means is we're allowed to repeat. Assuming no restrictions, how many possible zip codes are there? Well, if each position is a digit, not a letter, we have 10 different options for here, 0 through 9. That's 10 different options. And since there are no restrictions, we're allowed to repeat. There's another 10 options here, and 10 here, and 10 here, and 10 here, and so on and so forth. So this actually ends up being 10 to the power of 9, or 1 with 9 zeros after it. So there are 1 billion different zip codes. Possibilities. Alright, now if we've got a password situation. The password has 6 characters and is not allowed to have repeats. We can choose from the English alphabet or from the digits 1 through 9, not with 0. How many possible password choices does she have? So each position in the 6 characters, 1, 2, 3, 4, 5, 6, each position could be a letter or a number. So we have 24 numbers I'm sorry, 24 letters. Ooh, sorry about that. 26 letters. 26 letters. And the digits 1 through 9. The digits 1 through 9. So if we add 9 to the 26, we get 35. So these are all the letters and all the numbers that are possible for the first position, because we could have a letter or a number in the first position. Now, we are not allowed to have repeats, no repeated characters. So whether it be a letter or a number, we're not allowed to repeat it. Whatever we used in the first position, we can't use it in the second. And again. And again. And again. And again. So when you multiply all of these using the fundamental counting principle, she has 1,168, 675, 200 different passwords that she could come up with. Let's take a look at example 13. Marcus has 6 tickets to a Redskins game, but he only has 5 friends that can come with him. Now, that's 5 friends plus him, so that's 6 total people. How many different ways can the group sit in their seating section? When you're sitting people down, this means order matters. So in the first seat, Marcus and his 5 friends, that's a total of 6 people that could possibly sit in the first seat. Now that somebody sat down, only 5 people are available for the second seat. Third seat, there are only 4 people that could sit down, and so on and so forth. So 6 factorial is how we would solve this one. Or 720 different ways Marcus and his friends could sit in these seats. Alright, now that you had that, go ahead and attempt your homework and let us know if you have questions.